Okay, we are recording. So, here's about where we left off last time. We looked at this example, and we saw that we can take the formula from the previous page, interpret it appropriately to the variables being used, of course, and making extra sure not to forget that minus sign. Oh my gosh, can't emphasize that enough. Make sure to remember that minus sign. I know it's just a minus sign, and there's a temptation for people to think that's a sign error. Sign errors don't count for much. Absolutely not the point. What matters is what is the greater able confidently to conclude about what you understand about the material based on any given mistake, right? And so this minus sign is the sole distinguishing feature between absolutely correct and complete nonsense based on a fundamental misunderstanding of what's actually going on, right? So it's a huge error, right? And so you've got to make extra sure to remember that. It's just a good strategy, if nothing else. Okay, all right. So you take the formula. And you compute, you get an answer. So there's one last thing I wanted to say about all of this, and that is that most of the time that you see a question, this is another kind of a strategic point, you might say, the fact that the thing that you want to take a derivative of is, at least locally, a function, and therefore that you can, in fact, talk about its derivative, most of the time, that's not given. In this example, it was. Now, why did I feel free to give in the statement of this example that x is a function of y and z? Well, it's because a page previously, we did an example where we established in exactly this case that, in fact, yes, x is locally a function of y and z. So in some sense, we'd already done it. Right. So what I want to point out is on a more typical exam question, if you see an exam question that looks something like this, the more realistic, what you should expect phrasing would be like this. They'll just say, hey, here's a surface. What is the partial of x with respect to z? And if this is the statement of the question, well, it's not given that x is a function that we can even talk about taking the derivative of, right? And one could say that, well, that makes this a bad question. But here's the thing. This is how these situations will come at you in applications that y'all will see in engineering or whatever else, right? They won't give it to you, and they won't. I mean, again, this is just how, when you're dealing with a problem in the real world will not say, hey, by the way, you got to worry about the fact that x may or may not be a function, right? So life is going to come at you like this. And when you see a question like this, here's what you need to do. Just to be explicit, when you see this question, the very first thing you should do is all this stuff right here. You should ask, is x locally a function of y and z? And you should resolve that matter in the affirmative first, right? And then proceed to computing the partial derivative that you're interested in by, for example, what we did here. And so anyway, both of those are required to be able to answer a typically worded question. Again, no freebies given, right? You need to do both processes. You need to establish that x actually is a function first, and then actually compute the relevant partial. So now just so you know, past precedent, every question's different. I can't make any promises. Don't hold me to it. But typically in the past, these, what I'm going to call two parts of the question, about equally weighted in terms of grading. Right? So if you make the mistake of taking a question where it's not given that x is a function, and then just naively just treating it like it's a function, right? You probably just talked yourself out of about half the points on the question. Right? So don't make that mistake. Again, it's another landmine that you can accidentally step on, and please try not to step on that. Okay. Everybody on board? Everybody comfortable with all of this? Moving along. On to chapter 3. Of course, we've already done 3.1. So on to 3.2. 3.2 has various different topics in it, some of which are important to the course, some of which are, I'm going to say, kind of a digression and not really, it's just not as important to the course. And when there's so much to be done, it's not really quite going to make the cut for spending a lot of time in class. So what we're starting with, though, here is, this is actually really important. This is setting up some notation and a framework that we're going to be using massively. Not just in chapter 3 here, but really more importantly in chapters 6 and 7. This is going to be a really big deal. So it pertains to a parametric curve. Keep in mind, a parametric curve is, position as a function of time. So here we have our parametric curve, and you can talk about, on that parametric curve, right? You can talk about various different things. You can compute the velocity, right? The velocity is going to be some vector, like, I don't know, about like that, let's say. And then we can ask the very reasonable question, okay, given that, we are at this point, and given that we are moving with a certain velocity, in some amount of time dt, how much would I expect as I move along this curve, based on that velocity, how much would I expect my displacement to be in some amount of time dt? And I think this is a pretty easy pitch here, that my expectation of how much I will have displaced is going to be geometrically something like this. It's not going to be exactly, right? I mean, the curve itself actually curves. I mean, where will I actually be? Yeah, it's not going to be a perfectly something that's perfectly estimated by the instantaneous derivative, but it'll be pretty close, right? So geometrically, we expect the dx vector to be kind of like this. And computationally, velocity times time, right? That's how you compute displacement. It's velocity times time. Okay. All right. Which, of course, you could write differently, like this, if you like. Okay. Next question. Related question. Again, looking at this picture, let's ask the question, how would we, at least in a linear estimate, how would we estimate the length of that piece of curve? What I'm going to call ds. And my figure leaves a little something to be desired. I highlighted an actual piece of the curve itself, right? Of course, I'm not going to get the exact answer. I'm doing a linear approximation, right? But if I had to, based on what's going on at this point, given a certain velocity, given a certain time dt, how much distance would I expect that I've traveled? And I think a pretty reasonable pitch to make on that is, we've already linearly estimated the displacement, right? And if you have already linearly estimated the displacement, shouldn't the distance just be the magnitude of that displacement? Right? Again, I think that's a pretty easy pitch. Again, it's just an estimate. Again, it's not perfect, but pretty reasonable estimate. And by the way, another way to say that, keeping in mind that dx is v dt, pretty reasonable, I think, that magnitude is magnitude of v times dt. And of course, another way to say that is distance equals speed times time. Keep in mind, magnitude of velocity is speed. Okay, how are we doing on all that stuff right there? That all stand to reason? Seem plausible? These are very important formulas to make sure you keep in mind. By the way, this idea of the dx vector is something that takes a little sort of getting used to. Seems weird to have a differential that's a vector. Not sure we've seen that before. This might be our first time seeing a vector differential. Right? But if you think about it, all a differential is a linear estimate of how much something changes. This is a linear estimate of how much our position changes. So it is a vector and it is a differential. So there you go. Okay. All right. Next thing we want to talk about. When you have again, a parametric curve. Let me do a better job with have a parametric curve, and if we're moving with some velocity, we can ask a perfectly reasonable question, which is what direction are we going? And very often we represent directions by way of a unit vector. So the unit vector that points in the direction of the velocity ends up being a really convenient thing to have a name and a notation for, and so this is, we use capital T. And this is the unit direction vector. Capital T is pretty standard choice of notation for that. Easily computed, of course. It's just the unit vector pointing in the direction of the velocity, so of course it's that. Now, you'll notice over here that I have, let's see here, I have represented T in some algebra over here. There it is. The claim is that dx is t times ds. And let's talk about why that's true. So there's various different ways you can see it. One thing you can do, no problem, right? If you want to do a little bit of algebra, it's very little algebra, it's nothing to it. You could straight up take this formula for t right here and this formula for ds right here. Plug them into there, and dx is what you get. It just works, right? Algebraically, it's fine. So that's one reasonable take. Here's what I think is ultimately a more satisfying take. If you think about it, dx being as it is a vector, it has a direction and a magnitude. And let's just look at the dx vector. T is the unit vector representing the direction that dx points right there in the picture. And ds is the magnitude. So I think a pretty reasonable take is, why is dx equal to t ds? Well, because this is literally saying direction and magnitude, all immediately evident right there in the picture. So that's my preferred way of thinking about it. I find it more intuitively satisfying. Everybody's different. Whichever one you like, go for it. Okay, so with all of that said, that's really the most important stuff in this section, at least for the purposes of what we're going to do in this course. So everything else I'm going to do kind of quickly. Also, the other things that we're going to do in here are pretty plug and chug. And so I know y'all are really good at plug and chug, so let me just make a couple observations here. Let's talk about how to compute the total length of a parametric curve. There you go, the entire parametric curve. How would you compute the total length? Well, a pretty reasonable take would be to say, let's look at some little piece of the parametric curve, right? We already know how to compute what the length of that little piece is. ds is v dt. We could do this for every one of the little pieces. And let's just add up over the entire curve. So adding up all those little ds's gives you your total length s. Pretty believable, I hope. We can see this in action now. Looking at this example here. Oh, and let me go into the, yeah, there we go. So here's a parametric curve, range of values of t. How am I going to compute the total length? And this is some wacky curve, by the way. Look, the x formula is quadratic. The y formula is cubic. So this is a weird looking curve, right? The total length of it from t equals 0 to t equals 1. Well, again with the colors. Plug and chug. Compute the velocity, compute the magnitude of the velocity, integrate over the given range of values of t. There you go. Now you've noticed, I'm sure, the bad news. The bad news is this integral, nasty. Right? I don't want to have to do that integral. I think I probably could. That'd be a tough one though. Right? I'm sorry to report that this is how it tends to break down. And you can almost even kind of see why. Ultimately, it's because magnitudes are square roots. And so you're going to be, this is right there in the formula, you're going to be looking at an integral of a square root. And the stuff on the inside is unlikely to be super pretty because it's a sum of squares of things. Right? So yes, there are some highly tailored examples that make this work out nicely. Vast majority of the time, it's ugly. And very often, in fact, maybe even still vast majority of the time, intractable. You just can't compute it analytically. So that's unfortunate. So by the way, if you look on some of my old tests where you may find what's the length of the curve kind of questions, very often the question will say, write an integral in terms of a single parameter that represents the length. In other words, you don't have to compute the integral. Okay, yeah?
Why are you allowed to divide like everything by 2?
Do what now?
Why are you allowed to divide, like take out one of the t's? Like understand
Take out.
Factor. You see
Take out one of the.
integral, you have 2t minus 1 instead of t squared minus t.
Oh, because I took the derivative. Yeah. So the point is, this thing in here is the velocity, right? And so to compute the velocity, you've got to start with x and differentiate. Yeah. Okie dokie. Okay. Related point. I'm going to segue into this by making a silly example of what's called a reparameterization. So here's a parameterization of this curve. That's an easy plug and confirm. Right? You take the formula for x, formula for y, plug it in, the equation works. Right? Easily confirmed. Here's the thing. This also satisfies that equation. Namely, if you take this formula for x and this formula for y, it satisfies that equation. So what we have here now are two distinct parameterizations of the exact same curve. Now, hopefully this is not too surprising. Let me remind you of one of the big points of view on what a parameterization is. A parameterization gives position as a function of time. Namely, it tells you how to draw the curve. Because in the process of drawing a curve, the tip of your pen will be at a particular position as time passes, and for every value of time, you're at a new position. Well, there's many different ways to draw a curve. You can draw it quickly or slowly, or you can start off quickly and then slow down, or vice versa. Whatever. There's countless different ways to do it, and likewise countless parameterization. So I hope this isn't too shocking of a fact. The point I want to make about these two parameterizations is that one comes from the other, namely, this formula right here, t equals q cubed plus q. If you take that and plug it into there, you get this. Oh, I meant to, there we go. So this equation, if you have one parameter written in terms of another, when you plug that into your first parameterization, out comes a new, what we call reparameterization. Okay, so with that in mind, turns out there is a particular reparameterization that has some nice features. It's called the arc length parameterization. And keep in mind, if you have a parametric curve, again, here's a parametric curve, there is a point on our parametric curve. What parameter would I use to describe that point? Well, I could say that that's the point that you get at time t. I could characterize it by what time I get to that point, or I could characterize it by distance traveled from a fixed starting point. So let me give you a couple of hopefully relatable examples. If you're driving along a road, you are kind of parameterizing that road. And you're tracing out the road as you drive along the road. So, all right, well, you could keep track of your position as you take your road trip, and you could write down where you are, longitude and latitude, where you are on the map every moment in time, right? Or you could write down your locations as you drive along the road, indexed by what your odometer says. Right? And every time you click over another mile, you write down your location. Every time you click over another mile, you write down your location. Right? So that's the difference between these two different kind of parameterizations. Position is a function of time, and position is a function of distance. Okay. All right. So how do you relate these two things? Well, there's no problem. We have a formula that gives us distance as a function of time, right? And so given that you want to know, okay, all right, well, I'm at some point at time t, and I want to know what's the amount of distance. What is this s? How much distance have I covered by time t? Well, there's our formula. It's magnitude of the velocity, integral of the speed, whatever you want to call it. And there you go. You've got s as a function of t, and then just solve for t. Plug it into there, and out comes position as a function of s. And again, algebraically, this is a pain because look at these integrals. Right, this integral, again, it's got an integral of a magnitude. So that's going to be an integral of a square root. This is going to be an ugly integral. Very often in practice, you can't do this analytically, and that's a bummer. But there are some pretty nice things that happen if you either can do it or if you just start from the premise that your parameterization should be the arc length parameterization. First observation, I'm going to say it's intrinsic to the curve. This doesn't matter how fast you drive. Right? Drive slow, drive fast, drive choppy, whatever. However fast you drive, once you've driven 12 miles, you will be at the same point no matter how fast you drove to get there. Right? So this has got nothing to do with the driver. It's got nothing to do with the road trip. It's only about the road itself. So that's kind of nice. It's fundamentally natural. Another nice observation about it, it is a unit speed parameterization. And the best way to see this, I think, is to point out that and that come straight out of the chain rule. Just write down the chain rule. Take a magnitude of both sides. And notice these things I have circled in blue both represent speed. The one on the left says magnitude of the velocity. That's speed. The one on the right says distance per unit time. That's speed. Right? So there are two different ways of saying the same thing. And having made that observation that those are equal, that means that this must be 1, which is what I mean by saying that is a unit speed parameterization. Which you might call the velocity of position with respect to distance has magnitude 1. Okay, kind of cool. Useful in some situations. But we've already made the unfortunate observation, yes, computing this can be really inconvenient. And just for fun, I do have an example here, and I'm going to mostly wave my hands at it. This is a good exercise to read through, but you can see how it's pretty undesirable. And things get pretty ugly along in here, for example. Right? That's not looking like a friendly integral. Now, I've gone to some trouble, and I tailored a special curve here, right, that has a special velocity vector that when you look at the sum of the squares of the components, and you get this monstrosity. Look at this. Isn't this wonderful? This plus 4 tau squared just turns this minus into a plus, which makes this actually turns this from one perfect square into a different perfect square. Don't you love it when that happens? By the way, this is not the only time you're going to see this algebraic trick. This comes up significantly. I saw this dozens of times in my physics major, which means you're all going to see it several times, I think, at least. And so anyway, again, because of the highly tailored algebra, it turns out that this is the square root of a square, which turns into a reasonable integral. And you can actually compute this one. And even still, look at that relationship I got. I need to solve for t to do the reparameterization, and I don't know how to do that. So even in the almost best case scenarios, the integrals stink. So anyway, there you go. Okay, how are we doing? Is everybody on board? Okay. All right. Okay, on to 3.3. So vector fields are a new object that we're going to talk about. Turns out to be a really important object for understanding vector calculus. These are going to be the main object of study, arguably, when we get to chapter 6 and 7. So we need to have a clear, confident understanding of what these things are. And here you go, a vector field, what we call a vector field on Rn, is a function like this. So it's a function where the domain and the target are both Rn. Now, what does that have to do with these pictures? Well, these pictures are very specially tailored constructions intended specifically not only for viewing functions like this, but for viewing functions like this in a way that is maximum convenient for certain applications. And here's the big idea. Coming out of the domain, the input that goes into the function, you're going to view that input as being a point, such as I have there, such as I have here. So we're viewing the input as a point. And then the output that we get in the target, the output is going to be viewed as a vector, not as a point. Right? So this is a very important distinction. The input we view as a point, the output we view as a vector. You cannot see that in how this how the functional notation is written here. Rn to Rn, it makes it look like the ins and the outs are the same kinds of critters. Right? And importantly, they're not. Inputs are points, outputs are vectors. Is that cool? And then we draw the picture with all of this in mind. The inputs we've already observed, the inputs we've drawn as a couple of points, and then the outputs we draw as vectors represented by arrows where very specifically we put the tail of the arrow at the point that was the input point. Okay, so that's what a vector field is and how we draw this picture geometrically representing vector fields. Everybody on board? Everybody? We got several examples coming, but I just want to make sure everybody sees the process here. Okay, let's see here. A couple observations I want to make. First of all, why would we invent such an odd little construction? Right? Seems kind of arbitrary and awkward, strange. Here's why. Turns out that exactly this point of view on exactly this kind of function is exactly what we need to algebraically represent some very real-world natural phenomena. And the easiest one to see, in my opinion, is a fluid flow. Right? So you can just look at these arrows and you can almost imagine the fluid flowing along as indicated by the vectors. Right? And so in fact, there's a couple of different ways to do this, and we'll talk about some of those details in a few minutes. But if you have a fluid that is flowing, and you want to mathematically represent how a fluid is flowing, and at every point in your space, there's a direction that the fluid is flowing, and also either a velocity or something along those lines that represents how much the fluid is flowing in that direction. Vector field, perfect tool for doing that. And there are other instances of at every point there's a vector. Force fields. Right? Think about the gravitational field, for example. Wherever you might happen to be, there is a corresponding gravitational force represented by a vector. So, very different from a fluid flow, but actually still equally nicely represented with a vector field. So this is a very natural and valuable construction for real-world applications. At a quick glance, it seems like sort of, silly mathematician nonsense, but this is a very critical tool for real-world applications. Okay. second observation I want to make before we see some examples. These pictures, they're not graphs. Right? Y'all heard me say that a million times. You got to watch out for, wait a second, what kind of a picture is this? Don't try to take the calculus of graphs and apply it to a level set that isn't a graph. Right? It doesn't work. It doesn't make any sense at all. You get nonsensical, ridiculous answers and your bridge falls down. Right? So, what kind of a picture is this? Well, it's not a graph. These are not level sets. We're not parameterizing anything. It's not really what I like to call the literal picture, where we see the domain and target separately. We've had 4 previous kinds of pictures, fundamentally different kinds of pictures that we've drawn for multivariable functions. This is none of them. This is number 5 now, right? So again, reminder, you have to have conscious, crisp, stark boundaries in your head between the calculus that you understand for, let's say, level sets, and the calculus that you understand for graphs, and the calculus you understand for parameterizations. Totally different. And again, something you have to consciously make sure not to blur or blur in your mind. So yet another. And the calculus of vector fields, turns out there's some powerful ideas about the calculus of vector fields. That, in some sense, that's what Chapter 6 is all about, is the calculus of vector fields. Chapter 6 and 7, I forgot what I said before. Chapter 6 and 7 is all about the calculus of vector fields. Okay. All right, so that's why we care. Okay, a couple of examples. Here we go. Constant vector field. Right? Notice the field vector, the vector that we associate at any given point, always the same, always 2, 1. And so no matter where you are, always the same. So I think it's worth pointing out this, and it's not too hard to accept, I think, that this is what a constant vector field would look like. But notice it's really, really different from what you sort of expect things to look like, let's say, if you're talking about graphs, right? With graphs, you'd have like a horizontal, either a horizontal line, horizontal plane. You'd expect horizontal to figure prominently in the picture if you're looking at graphs. Here, nothing of the sort. Not horizontal, not even a little bit. Right? So again, keep these pictures different in your mind. Nevertheless, I think it is pretty evident in the picture that you get the same vector 2, 1 at every point, at every xy. Okay. All right, here's another example. Let's look at this right here. This one's a little bit of a tricky one. Let's see if I can squeeze that out. Yeah, there we go. Okay, so what this says is, at every point, x, y, keep in mind the input we view as a point. Point is a location. Okay. It says here that my field vector is also x, y. But keep in mind, the input, despite the input having been viewed as a point, the rule is, if you're talking vector fields, the output you have to view as a vector. So how can I take that input point and understand, ultimately the same thing, ultimately it, right, as a vector? And the idea is that when you have a point, there is the corresponding position vector. Right? So this is the vector, x, y. That's what this is. And so we draw the same vector there to represent the field. And now let me get this little crutch out of the way. So, input point, output vector, but they're algebraically the same. How are we doing? Everybody happy with that? So notice, that means that the field vectors here, all field vectors point, you'll notice, away from the origin. 2 seconds. Away from the origin, and the further the point is away from the origin, the longer the field vector is going to be. And so I claim with all of that in mind, this single instance that we drew generalizes to something like this. And notice all these vectors, again, pointing radially away from the origin, and the farther you are away from the origin, the longer the field vectors are. Yeah, go ahead.
What is that vector from the origin to the input point?
One more time.
The vector going from the origin to the input
Oh,
point?
yeah, that's right. So let me go back to here. Yeah, so that is the position vector for the point x. Right? So you might say, for example, let me just clear out all the rest of this stuff. This input, you can view it in either of a couple of ways. You can view it as a point, or you can view it as a vector. We're supposed to view it as a point, but I'm momentarily choosing to say, it's also kind of nice to think of this as a vector, because frankly the output is this viewed as a vector, and so it's just helpful for me to infer the picture. Yeah. Okay. All right. Okay, let's see. Another example. This one's a little trickier. By the way, you may notice the last two examples that we looked at were kind of by hook or by crook, right? The methods that we used in those two previous cases, they don't really generalize, right? And this is just kind of the nature of the beast. When you're trying to understand vector field, there is no single process that will always result in the nice, crisp picture representing your vector field. Every vector field is different, and you have to kind of use, again, going back to that old metaphor, tools in your toolbox. Right? So I'm showing you different examples where we use different tools, and you're going to have all these tools at your disposal. Okay, again, point x comma y. Here's my field vector, negative y comma x. What can I say about that field vector? Now, there are a couple observations you can make. Now, again, peculiar to this example, but notice these two vectors, same magnitude. Right? I'm just saying, they're the same magnitude. Again, these two vectors, orthogonal. Easily confirmed. Take a dot product, you get 0. So that means that they're perpendicular, other than the origin, which is, of course, just one point. We don't really care about that. These vectors are perpendicular. So the field vector is perpendicular to the position vector for your point. And if you think about, okay, well, here's my position vector for that point. What are the two vectors that are perpendicular and have the same magnitude? Well, there's that one, and there's this one, and you can tell the difference. Which one of these should it be? You can tell the difference just by literally, picking a point and plugging it in and just seeing what that vector happens to be. And in this case, it is that one. Yep.
Is this used to describe a vortex?
Yeah, this is a kind of a vortex, absolutely. This is there's various. A complicated story ensues, right? This is a gentle vortex, right? Because if you look at what's happening at the origin, it's rotating slower and slower, right? The closer you get into the middle, the less is happening. So it's not like a tornado, right? Yeah, absolutely. So kind of our first example. Yeah, good. Okay, now here is another way to think about it, and I encourage you all to do this. This is an important skill that everyone in this class should have. This is a linear algebra take on this, and that is right here. This function that represents our vector field is a linear transformation. Eyeball that function and note that it is, in fact, straight up, that's a linear transformation, right? And furthermore, I can tell you geometrically what that linear transformation is. It's a rotation, a quarter turn counterclockwise around the origin. And that's something I want to make sure that everybody in this class knows how to conclude. Now, how are you going to do that? I'm going to hit the highlights for you, but I want you all to go through the details because, again, I think this is something that you got to have your hands on. You got to get some dirt under your fingernails to make sure that not only can you understand someone else doing it, but that you can personally do it. Right? So here's the big idea. This is clearly a linear transformation. Linear transformations are understood by matrices. Matrices could you could argue, are entirely determined by what are their column vectors, and columns are images of standard basis vectors. Right? So all you got to do here is just take this idea of a quarter turn counterclockwise, do that to the two standard basis vectors. Here they are, right? E1, E2. Do that geometric process, quarter turn counterclockwise. See what E1 turns into, see what E2 turns into, write that down, multiply it out. This is what you get. Right? So, again, make sure you can do that. If you get stuck, if you're not sure, if you didn't understand what I just said, if a gap of some sort that makes you unable to actually complete that, come to my office hours. I'll be happy to walk you through it. No problem. But do one way or the other, make sure that you can do this, because that is going to be assumed and expected for the rest of this course. Okay. All righty. Continuing, more examples. This is a good one. Most efficiently written down like that, but still not my favorite way to do it. I would rather write it down like this, and you'll see why momentarily. If I look at this expression that I've got here for this vector field F, easy first observation is that that's a unit vector. More importantly, that is a unit vector which, wherever you might happen to be, is pointing exactly away from the origin. Because I've taken the position vector x and just scaled it by dividing it by its own magnitude. Right? So position vectors always point away from the origin. Well, of course. So therefore, this green thing is a unit vector pointing away from the origin. Okay, so this is what we're going to call the radial aspect of it, because the direction that this vector field points is always away from the origin. I think radial is a natural choice of words there. Yeah?
So if the constant c is bigger than 0, is it still pointing?
Yeah, that's right. This c could be either plus or minus. I drew the picture here where c is negative, but it could be positive also, and then it would just be radial outward instead of radial inward. Yeah, totally. Okay, so radial means that. What would we say about this? The reciprocal of the square of the distance from the origin. Well, that's what we very commonly call an inverse square expression. It's pretty common terminology. So you write it in this way, the way I have circled in blue here, and again I have a preference for that over this, and they're the same, whatever, right? But if you write it like this, you could just literally see right here in the expression why we call this a radial inverse square vector field, or sometimes people say inverse square radial. Sometimes people just say inverse square, and they're like, come on, you know what I'm talking about. And the radial is implied. But I like to go ahead and say it. So radial inverse square. All right. So it turns out these are very common vector fields to need to understand. One very common situation is if you want to talk about a gravitational field, right? We're surrounded by gravitational fields. We live on a planet because of a gravitational field, right? You take away the gravitational field, we float off into space, right? I mean, this life depends on gravitational fields, so kind of a big deal. But a lot of people make the observation that, come on, I don't really need to understand gravitational fields. I'm not going to be an astronaut, right? I'm planning to stay on planet Earth for my entire life, where the gravitational field is a constant. Constants are easy to understand. Who needs it, right? So my counter argument is that, well, guess what? It's also exactly the structure of electric fields. Exactly the same structure. And all engineers, whatever type of engineer you're planning to become, definitely going to have to understand electric fields, right? So that's what this is also. This is the structure of an electric field. The constant would be positive instead of negative, but still, same structure. Okay. Everybody good? Okay. All righty. Another observation. This is a pretty straightforward observation. We've talked previously about gradients, right? We know gradients point uphill on the graph, right? What I have not previously observed is that gradients are actually vector fields. And we didn't have any particular need to previously. We didn't have any context for doing it. We didn't know what a vector field was before today, right? So, yeah, so that's why I didn't bring it up. But just look at what you get if you take some real valued multivariable function, and if you compute its gradient, you get a vector for every x and y. You get a vector for every point. You get a vector field. Now, again, there's nothing really particularly new here. It's a new take on this object that we've already studied quite a bit. Okay, so that just needs to get pointed out. All right. Now let's talk about terminology. This is a little bit unfortunate, but it is what it is. I'm going to start off with what I think is the natural terminology, what makes the most sense to me, and I'm going to segue into this by reminding y'all from single variable calculus. When you take a derivative, the result that you get from taking a derivative, we call it the derivative. Of course, what a silly thing to say. Okay, when you undo that, when you say, okay, yeah, I've got the derivative and I want to reverse engineer and find what was the thing whose derivative gave me that, we have a word for that too. It's antiderivative. Perfectly natural terminology. You're undoing the process of differentiation. So derivative and antiderivative, very common, very natural terminology. So I say the same for gradients. If you have some function, when you take a gradient, the result we call the gradient, of course. And likewise, if you undo that, if you take a vector field and ask, okay, yeah, what was the function whose gradient gave me that, I think we should call that the anti-gradient. Does that seem like a reasonable choice? Okay. So this is my preferred term. I'm going to be using the term anti-gradient throughout this course. Not quite exclusively, but I think it makes loads of sense. I think it's the best term for what we're describing here. Now, FYI, just so you know, most of the time outside of this class, you're not going to hear the term antigradient. You're going to hear the term potential function. Now, let's talk for a moment about why, what is the origin of this term potential function? The origin is this fact right here. And for example, with gravity, let's just think about gravity as a most common example. Y'all know about gravity. Gravity is a force and it points down. Right? Again, thankfully, can you imagine? What if gravity pointed up? That'd be a problem, right? Okay, gravity points down. The force is down. Let's think about potential energy, though. Gravitational potential energy. Y'all probably recall from high school physics. Gravitational potential, you have more potential up high, you have less potential down low. Right? Because when you're up high, you have the potential to create kinetic energy. You drop it, and then it creates a lot of kinetic energy as it goes further down. Okay, so how would we represent potential energy algebraically? Well, if you just think about what we just said, it's going to be some constant times altitude, right? Constant times z. And if you take the gradient of constant times z, you get up. Right? So the gradient of potential energy points up, the force, the actual force is down, and so that we cannot say that that force is the gradient of potential. It's not. They point in opposite directions, and so we fix that by putting a minus sign right there. So potential energy is just not the the anti-gradient of a force. It's the negative of the anti-gradient of the force. So, given this circumstance, I mean, here's my beef with the idea of using the term potential function. You're using a term that explicitly sweeps a critical minus sign under the rug, and that just gives me the willies, right? Now, don't get me wrong. I got it. I understand. And when somebody says potential function, I know what they mean, right? I'm aware of that minus sign, and I won't mess it up, right? But for students that are learning for the first time, this is an easy thing to mess up. And I also complain that this only makes any sense at all if your vector field is representing a force. In other words, if you're doing something physical, and plenty of math is not physical, right? So to me, this is awkward and narrow to call it a potential function. And so you give me my choice between awkward and narrow or natural and obvious. I'm going with natural and obvious myself. But anyway, be aware of both of these terms, and I guess we're out of time, so we'll draw the line right there. See y'all on Friday. Y'all have a good one.